Welcome to the studio animation about the heap sort algorithm. Heap sort is a comparison based sorting technique that uses a binary heap data structure. A heap is a special tree based data structure that satisfies the heap property. In a max heap for any given node I, the value of I is greater than or equal to the value of its children. In a min heap, the value of I is less than or equal to the value of its children. Here is the step-by-step demonstration on of building a max heap from the array 6, 5, 3, 1, 8, 7, 2 and 4 and arranging its element in a max heap order. We will start with the initial unsorted array and transform it into a max heap using the heapify process. To build a max heap, we need to adjust the array so that each parent node is greater than or equal to its children. We'll work from the bottom non-leaf nodes upwards, ensuring the heap property is maintained at each step. The array element will be represented in a binary tree structure where each parent node has two children. Let's begin with the initial step, considering the array as a complete binary tree. The first element 6 is already at the top, but let's focus on building the max heap by starting at the non-leaf node. We begin with the node at index 3, which is 1. This node has a left child 4 and no right child, so its position at the end of our tree representation. Since 4 is greater than 1, we swap them to ensure that node 1 satisfies the max heap property. The array now looks like this: 6, 5, 3, 4, 8, 7, 2 and 1. Next we move to the node at index 2, which is 3. This node has two children, 7 on the left and 2 on the right. Since 7 is greater than 3, we swap 3 and 7 to maintain the max heap structure. The array is updated to 6, 5, 7, 4, 8, 3, 2 and 1. We now shift our attention to the node 5 at index 1. This node has two children, 4 on the left and 8 on the right. Since 8 is largest, we swap 5 with 8. Our array now becomes 6, 8, 7, 4, 5, 3, 2 and 1. Finally, we heapify the root node at 6 at index 0. This node has two children, 8 on the left and 7 on the right. 8 is the largest among them, so we swap 6 with 8. The array becomes 8, 6, 7, 4, 5, 3, 2 and 1. The max heap is now complete. Each node in the heap satisfies the max heap property where the parent node is greater than its children. In summary, the max heap transformation process rearranges the element of the array into a binary heap, effectively preparing the data for the next step in the heap sort algorithm. By visually representing each step and swap, we ensure a clear understanding of how the max heap is built from the given array. Also, it ensures the property of the heap sort algorithm is satisfied in every step. Let's now see the overall algorithm for max heap. To start with blue. Through each element in the array, for each element array of I in the array from index 0 to n-1, insert the element array of I into the heap. Increment heap size by 1. Maintain max heap property pre-collate up to main inserted element. While current index is not the root, that is current index GT0, and the element at the current index is greater than its parent. To calculate parent index, check a parent of the current index is located at the index. Current index minus 1 divided by 2. To compare element with parent, check if heap of current index is greater than heap of parent index. Swap heap of current index with heap of parent index, then update current index set. Set current index to parent index, move up the heap. Continue this process for all elements in the array of. Coming to the end of the insertion, the array heap of now represents a max heap where every parent node is greater than or equal to its child node. Thus, the max heap property is maintained throughout the heap. The time complexity of a max heap is an important consideration when evaluating its performance for various operations. Insertion to the insert new element into the max heap and maintain the max heap property by percolating up. Time complexity order of log n. When inserting an element, it is initially placed at the end of the heap. In a binary heap, the height of the heap is at most log n, where n is the number of elements. Therefore, at most log n swaps are needed, resulting in a time complexity of order of log n. Deletion. To remove the maximum element from the maxim and restore the maxim property by percolating down. Time complexity order of login. The maximum element is located at the root and its removal involves replacing it with the last element in the heap. Similar to the insertion, the number of swap is bounded to the height of the heap, which is log n, leading to a time complexity of order of log n. Building a max heap to convert the unsorted array into a max heap using the heapify process. Time complexity order of n. Conclusion. The max heap is a powerful and a versatile data structure that efficiently manages dynamic set of data. With its ability to provide fast access to the largest element, the max heap is ideal for applications such as priority queue, where retrieving the maximum element is essential. The max heap robustness makes it an ideal choice for implementing the heap sort algorithm, where sorting an array is achieved in order of n log n time. This operation leverages the max heap property to ensure a reliable in-place sorting mechanism. Overall, the max heap is a fundamental data structure with applications extending to various fields, including graph algorithm and real-time systems. By balancing the time complexity with practical efficiency, the max heap remains an essential tool for developers and computer science.